Alright people, we're going to take a look at the section that was dealing with solids and liquids and gases. Alright, so this is our first section in the states of matter section. So let's start out with solids. Alright, a solid by definition is going to be an object that has a definite shape and a definite volume. Okay, so it has a definite shape and definite volume. So let's take a look at a solid. Let's just take your table that is in front of you right now, and if we were to look at the molecules or the particles that are making up that table, what we'd see is that they are in what we call a fixed position, meaning that they are very, very close together, and they're vibrating back and forth and up and down, so they are making constant contact with each other. And so we say they're in a fixed position because of the fact that you cannot take your hand and pass it through there without having to generate a certain amount of energy. And so this is a definite shape. It has a shape whether it's sitting on your table, or if it's in the classroom, or if it's outside. It's going to maintain that shape unless we do something different to it. So definite shape. Can't take your hand and pass it through it without a certain amount of energy that's going to cause it to crack and break the molecules that exist between there. And what we mean by volume, if you remember volume, it's the amount of space that the object is going to take up, and we said that we can measure it through regular shapes and irregular shapes, and regular shapes were length times width times height. Irregular shapes are going to have the water displacement, where you have to fill up the water, put the object in there, and then subtract your new mass from, or your new volume from your old volume. So these guys are going to have definite volumes and definite shapes, and so the particles are going to be close together. Now when we say the word definite, what we're really getting at is in that present moment. So if we take a pencil, for example, time for a banished drawing, and there's your pencil, and if we start out with this amount of volume, over time, as you take it to the pencil sharpener and you begin to cut away at that pencil, what you're going to discover is that the volume amount is going to change. And so definite in the present moment. Alright, so solids have a fixed position. They are definite shape, definite volume. Doesn't matter if we take this and move it wherever, it's going to maintain that same amount. Excuse me. Alright, let's move on to liquids. Liquids are another, and by the way, we should say that these are the states of matter. Okay, so that is what solids, liquids, and gases are. A liquid, by definition, is an object that is going to have a definite volume but no definite shape. Alright, so let's take water, for example, and let's put it into a beaker. So inside here is going to be our water. And so if we take this water and we put it into a smaller graduated cylinder. Okay, so this is going to be our graduated cylinder, and we take and we put this water in there. It is going to maintain the same volume. Whatever it was in here, let's say that it was, let's just do 10 milliliters, and we've put it in here, it is going to still remain 10 milliliters, even though we had gone from one container to the other. So that's telling us that it has a definite volume. The shape, however, may have changed. Here it might have been looking where it's you know, a larger amount, it looks like there is, or a smaller amount over here and a larger amount over here. We really see this when we change going from one object to another, where we could potentially take, trying trying to think of a good example for you. Let's take a swimming pool. All right. So if we have a square swimming pool, and let's say that for some reason we build this crazy star-looking swimming pool. All right. What's going to happen is whatever amount, which is the volume, that's in the square swimming pool goes into our very cool star swimming pool. It's going to be the same amount. It's going to look different because of the fact that it has a different shape to it, but it's still going to maintain the same. And the reason why it's able to maintain this different shape is because of the fact that the particles are a little bit further apart compared to our solids that we saw before. And so there's a little bit of space in between here that's created. And because of that space, we say that it is able to move freely. So it's able to move freely. And if it's able to move freely, it means that things can pass through it. If you've ever taken your hand and put it in the water and swayed it back and forth, and you were moving the molecules back and forth, or if you were jumping into water, obviously you're able to jump into the water and not experience the solid effect. Obviously that would break your back if you were to jump into some type of pool that was a solid, versus the liquid form that we're most comfortable and use. Now we break down liquids a little bit further, so let's go back and look at liquids as how easily it moves. Alright, so let's say liquids, and how we said that it has a definite volume but no definite shape. But we base a lot of our liquids on how easily something can flow. And so we'll refer to things like that as being a fluid. A fluid is a substance that flows. Okay, and so when we think of like an example of water, or if we were thinking of an example of honey, all right, these are two liquids. And what happens is that we know that if you were to take water from this graduated cylinder, all right, and we were to pour the water out, it would flow very easily. All right. If we were to do the same thing, let's make a bigger graduated cylinder here, with honey and try to pour it out, we know that the water would flow easily and the honey would not flow easily. And so we give this a fancy term called viscosity. And viscosity is ultimately the resistance to flow. Okay, so before we said that a fluid is a substance that flows. So we're saying is that it is a resistance to flow. And we'd say that honey has a higher viscosity or a greater resistance to flowing versus water. All right. Another property of water that we have looked at was in a lab that we did where we had a penny and we continued to add water drops until eventually what we saw is that this kind of made a dome shape to it, and it was actually hanging off the side of the penny without even dropping down to touch the table. And the reason for that is that there was an attraction that was occurring between the molecules that were at the surface and with the molecules that were just below them. And so this attraction that was created is called surface tension. And surface tension is going to be an inward pull among molecules And so that is what surface tension is. It's an inward pull among molecules that bring molecules on the surface closer together. And so there was an attraction here. Let's switch the colors so you can see it here. So there was an attraction between the molecules from the top and the bottom and from the sides. And so we start to see that there's this traction. And if you look very closely at the top of some water, you would see that there's this thin kind of membrane that exists, and that right there is what we call surface tension. All right, so that is liquids, and we're on to our final group, which is going to be the gases. All right, gases by definition are going to be no definite shape and no definite volume. Alright, so they have no definite shape and no definite volume. And gases are going to be, in terms of particle position, they are going to be the furthest apart. And since they are the furthest apart, they are going to take the shape and the volume of whatever container that they are in. So let's take our room for a second, our classroom. Alright, so here's our room. And this will be our door into the room. And so what happens is that air is ultimately a mixture of gases, and those gases that are going to be in the room are going to expand out. And the only thing that's going to stop them from continuing to expand are these walls. The walls are going to prevent that gas from continuing to expand, because remember, it's taking the shape of whatever container that it's in. It doesn't have a definite shape, so whatever space that it is in, or if we take a propane tank, let's do a propane tank here. There's your propane tank. So what happens is that the propane is going to expand, and the only thing that's going to keep it from continuing to expand are the container walls of the propane tank. Same thing with our classroom of air that's on the inside there. And so it has no definite shape. The volume is based on whatever the container's volume is. So we could say that it is going to take the shape of the container. So it's going to take the shape of the container that the gas is in. And we can also say that it's going to take the volume of the container that the gas is in. Okay, so what we discover here is that the shape and the volume is equal to the container the gas is in. Alright, so solids, liquids, gases, all states of matter that are very important.